Today we have Professor Frederico Fiúza from our department, from IPFN, like the speaker from last week. So Frederico was a student here in his undergraduate. He had some brilliant people teaching him.
Yes, particularly analytical mechanics.
And so he then did his PhD here, if I'm not wrong, and then had a brilliant career in the US, culminating in being group leader at Stanford. Stanford is right? That's luck, yeah. And then something happened that decided to return to Lisbon, which made the department here very, very happy. I think it was the weather. No?
Weather and COVID.
Weather and COVID. And it was still before some election. So Frederico works on many things, and I think you will get today an overview of the work that he has done and the ability to be relevant in different areas, to bring things together. Thank you very much for accepting this, and the floor is yours.
All right. Good afternoon, everyone. First of all, thank you, Guilherme, for the kind invitation. It's a pleasure to give this physics colloquium. The idea for today is to tell you a little bit about some of the work that we are doing here at IST in the context of a European Research Council project, where we are trying to understand the basic mechanisms behind some of nature's most powerful accelerators. Coming at an angle that is complementary to astrophysical observations. In particular, we are trying to use first principle plasma simulations and laboratory experiments to try to resolve some of these underlying physics on scales that we cannot probe directly from observations. Okay? So before I start, quick show of hands. How many of you has heard about cosmic rays before? I expect everyone. Okay. How many of you has heard about particle acceleration in astrophysical shocks before? Okay, maybe a third or a half. Okay, so I think it's good that you came to this presentation. I'll hopefully by the end you will connect these things more closely. All right, so let me start by acknowledging many people that have contributed to some of the work I'll show you today, starting with my current and former group members. Many of the students and postdocs working on this are here in the audience. My colleagues at the Lawrence Livermore National Lab and the National Ignition Facility at Livermore. The experimental results I'll be showing you come from a long collaboration we have over the past 10 years or so. And also many of my international collaborations that have shaped the thinking about this project. So since you all heard about cosmic rays, as you know, cosmic rays are energetic charged particles that bombard the Earth's magnetosphere from outer space. In the last 100 years or so, since the first balloon experiments from Victor S. in 1912, until today, there's a great deal more that we know about cosmic rays, and they're very important in actually as a window of the energetic universe. We know relatively well their composition. They're primarily composed by protons, although they can also have heavier nucleus and electrons. We detect them either directly with space-based instruments or indirectly with ground-based instruments such as the POG Observatory. I see here Professor Ruben, of course in LIP, they do a great deal of work involved with these observatories and the study of these cosmic rays. Another thing that we know quite well is the spectrum of the cosmic rays that we measure. And it's quite remarkable. You see here a spectrum that spans more than 10 orders of magnitude in energy, okay, going all the way to 10 to the 21 electron volts. And you see that this spectrum is quite remarkable, resembling a power law spectrum across this entire range of energy. So the flux is a power law dependence of the energy of these particles. In reality, there are some changes in the slope of this power law, but this is quite remarkable. The most energetic cosmic rays detected are above 10 to the 20 electron volts, about 160 joules, okay? So this is the energy of a baseball moving at about 100 kilometers per hour packed in a tiny particle, okay? So it's quite remarkable that these astrophysical accelerators, whatever they may be, they are able to channel all this energy into a single particle. And so despite quite a lot of progress and study over the last 100 years, we still don't fully understand what is the origin of these very energetic particles, okay? Of course, based on the abundance of sources, based on the energetics, we can constrain their sources to some systems. These include, for example, supernovae, so massive stars that explode and release vast amount of energy into the ambient medium. They also include very energetic relativistic jets and gamma ray bursts. Gamma ray bursts are the most powerful explosions in the universe, okay? They can release in a fraction of a second as much energy as the sun will emit in its entire 10 billion year lifetime. But we still don't understand where exactly different parts of the spectrum come from and what are the underlying mechanisms responsible for such efficient acceleration. We know that these environments are in a state of matter that is a plasma. I hope that most of you, since there's also a colloquium about plasmas last week, have heard about plasma. So this is the fourth state of matter. When you heat the gas to high enough temperatures, you start ionizing this gas, so separating the electrons from the nucleus, and you are left with this soup of charged particles and electrons in protons or ions that interact electromagnetically, okay? And so we know that these plasma processes must be responsible for controlling how the energy is partitioned in these systems. In particular, how some of the energy of this system ends up in a few very energetic particles, and these particles also may emit radiation that we detect as well. And so the goal of this talk and of the work that we've been doing is trying to understand what exactly are these processes and how they manage to be so efficient at accelerating these charged particles. One of the most important factories of energetic cosmic rays, at least within our galaxy, are supernovae, okay? So when you have a star that runs out of fuel, is going to undergo gravitational collapse, and as it explodes, it's going to release vast amount of energetic plasma, so charged particles, into the interstellar medium, which is also a plasma. And that as this energetic plasma propagates in the ambient one, it drives very strong shock waves. Okay, this is an image of one of these supernovae. It's a composite with X-rays and radio. And what you see is these very bright X-ray rims at the edge of this supernova remnant indicate the formation of a very strong shock. This is a sharp discontinuity in the pressure and the density and the temperature of the medium as these shock waves propagate through the medium. And so there's significant consensus that at least up to the knee, or energy slightly above the knee, cosmic rays are likely coming from supernova within the galaxy. These accelerators can reach energies that are orders of magnitude above what we can do here on Earth. Even in the largest accelerators, like the LHC, where we produce about 10 TeV, we are a few orders of magnitude below what these supernova remnants could produce. And so we want to understand how exactly these supernova remnant shocks manage to be so efficient in producing these energetic particles. Astrophysical shocks have actually been long seen as powerful particle accelerators. Starting with the studies of Earth's bow shock, so that's where the solar wind meets the Earth's magnetosphere, to some of the largest scale shocks that we can encounter associated with galaxy clusters. As entire clusters of galaxies collide with each other, they form collisionless shocks on very large megaparsec scales. These shocks are special in the sense that they are different from other shock waves that you may be more familiar with, either in the atmosphere, for example, as a plane drives faster than the sound speed, or as you try to compress some material. These are typically hydrodynamic shocks that are mediated by binary Coulomb collisions between the molecules of the air, okay, or of the material. These shocks are collisionless in the sense that Coulomb collisions are too rare between charged particles to be able to be responsible for the slowdown and the compression of these plasmas, okay? There was a long discussion about this in the 40s and the 50s, which was finally put to rest with the observation and the characterization of the Earth's bow shock, okay? So when the solar wind emits, so these energetic particles emitted by the sun towards the Earth, when they meet the Earth's magnetosphere, they're going to be slowed down and compressed to form a shock, and the width of this shock is about 100 kilometers, where the Coulomb mean free path is about 1 astronomical unit. Obviously, this is not to scale, okay? So there's no way that the compression associated with this shock is due to Coulomb collisions. What we now understand is that this is due to plasma processes. It's the fact that as these energetic charged particles stream on an ambient plasma, they are going to excite electric fields and magnetic fields due to plasma instabilities, and it's these electromagnetic fields that will act as collisions. They will scatter these charged particles to slow them down and to produce these shock waves, okay? And so this is what we want to understand. What's the physics? What are the processes that dictate the formation and the ability of these shock waves to efficiently accelerate particles? By the way, the same is true in most astrophysical shock waves. This is again an example of a supernova remnant, where you also infer that the Coulomb mean free path is orders of magnitude larger than the thickness of the shock wave that is inferred. Now, our ability to characterize these distant shock waves come primarily from the light that is emitted. In the case of the Earth's bow shock or planetary shocks, we have spacecrafts that can do in situ measurements. These are typically limited to low Mach numbers. Mach number is basically the ratio between the velocity of these shocks and the ambient, the velocity at which the ambient medium propagates information, like the sound speed, okay? When this is low, typically these shocks are not very powerful accelerators, like in planetary magnetospheres. But in astrophysical shocks, these Mach numbers tend to be very large, and our information about those ones is much more limited. One of the most important sources of information is the radiation that is emitted by accelerated charged particles in these environments. As you know, if electrons, or protons, but in this case electrons, are energized in the presence of strong magnetic fields, as they gyrate around these magnetic fields, they are going to emit synchrotron radiation. We can use this radiation to observe these environments and to learn more about both the energy spectrum of these accelerated electrons, but also the presence of strong magnetic fields in these environments. And so one of the things that we can say based on this type of observations is to quantify the magnetic fields present in these shocks. This is because for a given band, energy band in the X-rays, for example, that we detect, we see these very sharp rims. This is the radial profile of these, of the brightness of these rims in the X-rays. And because this is very short, to explain this, we must have very strong synchrotron cooling. So these electrons must be radiating a lot in the presence of these strong magnetic fields in order to explain such a narrow X-ray rim. Based on this, we can infer what is the amplitude of the magnetic fields in the location where the electrons are being accelerated. And we infer that this is of the order of a few hundred microgauss. The interstellar medium magnetic field is a few microgauss. And so this means that these shocks are able to amplify ambient magnetic fields to values on the order of 100 times the ambient field. So, okay, we know that they are good at amplifying magnetic fields and are good at accelerating charged particles. So how do they manage to do this? The most important idea behind shock acceleration dates back to Fermi in the late 40s. Okay, Enrico Fermi realized that if you have interstellar magnetic fields with some random motion, okay, charged particles interacting with these magnetic fields will have a slight advantage in gaining energy versus losing energy. So if you consider the random motion of a charged particle interacting with some magnetic clouds, You can show that if this particle collides head-on with this cloud, it's going to gain energy, as you know. If it's head-off, it's going to lose energy. But on average, head-on collisions are slightly more probable, and this gives you an energy gain on average, okay? This energy gain turns out to be of second order. So it's proportional to the velocity of these magnetic clouds divided by the speed of light squared, okay? So this can be a powerful mechanism for accelerating particles in strong magnetic fields, but it's not very efficient for non-relativistic plasmas, as are the cases of supernova remnant shocks. When I say that these magnetic fields are accelerating particles, does this tickle some of you? I mean, we know that magnetic fields don't do work on the particles, right? Well, if you have magnetic fields in a conducting fluid, like a plasma, that is moving, this is going to produce an electric field, okay, which is given by the cross product between the velocity of the fluid and the magnetic field. So this is actually the electric field that is giving energy to the particles. So if you have this disturbance in the magnetic field that is moving with some velocity, there's going to be an electric field associated with that, and that's how the particle gains energy as it scatters from that field, okay? Okay, so this looks quite interesting. So particles can gain energy as they interact with these magnetic disturbances, but it's not very efficient in non-relativistic plasmas. About 30 years later, 4 independent groups realized a way of making this very efficient when associated with astrophysical shock waves. The key idea here is that in a shock wave, by definition, you have converging flows. So you have a gradient in the velocity of the plasma, okay? So now let's do the same exercise where we have some magnetic disturbances around the shock wave, so both ahead and behind the shock wave. Let's say the shock wave is moving to the right, but here we are in the frame of the shock. So the plasma that is ahead of the shock wave is moving to the left towards the shock, and the plasma behind is moving to the left, so moving away from the shock. But because there's a gradient in velocity, the plasma moving towards the shock is faster than the plasma moving away from the shock behind it, okay? So now if a charged particle is doing the same thing as Fermi considered, so if it's scattering back and forth, interacting with these magnetic fields, now its ability to gain energy is going to be first order, because every time the particle goes to the right and comes back, it gains energy. Every time it goes to the left and comes back, it loses energy, but it always gains more energy on this side than it loses on that side, okay? So this becomes much more efficient if you are dealing with non-relativistic shocks. It turns out that the fractional energy gain of the charged particles in every cycle around the shock is proportional to the shock speed over the speed of light, and the fractional particle loss per cycle is also proportional to that. So the particles don't stay trapped forever in this shock. There's a probability that they will diffuse along these magnetic fields and get lost. But because they have the same dependence, it turns out that the spectrum that results from this process is a power law. More important than that, the index of this power law only depends on the compression ratio, or the jump in velocity that these particles experience in the shock. Now the beauty here is that for strong shock waves, and when we say strong shock waves, we mean that the Mach number is very large, so the velocity of the shock is much, much larger than the ambient sound speed, for example. This ratio is fixed, is about 4, okay? And that gives you a fixed index in the energy spectrum of e to the minus 2, okay? So this is a beautiful solution for the cosmic ray acceleration and the power law spectrum that is universal in the sense that they may have shocks in very different systems, provided that they are strong shock waves, they would give you a similar power law index. Now, of course, this was immediately very well received and has been the main theory behind cosmic ray acceleration in astrophysical shocks. However, it's important to note that this is a test particle based solution, okay? So we are assuming from the beginning that we have some perturbations in the magnetic field that are capable of scattering these particles. These particles are capable of crossing the shock back and forth, and in such conditions you develop this type of spectrum. Unfortunately, it is not obvious how this happens, how you produce the required magnetic field perturbations that you need for this to be efficient. If you think about the cosmic ray spectrum, there's a very wide range of energies, okay? If you think about a uniform magnetic field, or magnetic field line, a straight magnetic field line, charged particles, if they are magnetized, they're going to be primarily going around this field line, okay? So if the field line crosses the shock, they're just going to cross the shock as well and be lost behind the shock. For particles to efficiently diffuse or scatter in these magnetic fields, you need to have modulations in this magnetic field line that in terms of amplitude are large. So delta B over B is large. So the level of this fluctuation is large compared with the mean magnetic field. And the spatial scale associated with these modulations, the wavelength if you want, needs to be of the order of the gyro radius of these particles. That's where the scattering is going to be most efficient, okay? You can think about this, that if the wavelength is very long, compared to the Larmor radius of the particle just sees this as a uniform field. At the scale of its Larmor radius, it cannot understand that there is a modulation in the field, okay? And so, we know that these plasmas can host a zoo of instabilities that operate at different scales, from the small kinetic scales of the plasma down to the very large scales. But how these work with each other in order to make this efficient across a wide range of energies, we still don't understand. So this is one important puzzle. Another very important puzzle, perhaps the biggest puzzle in this shock acceleration, is the injection of electrons. In the description I was giving you before, we were looking at this shock front as something that is infinitely thin. So a very sharp transition between what is in front and behind this shock wave. In reality, it has a thickness that is of the order of the gyro radius of the ions, okay? If you think about the plasma flow propagating through a shock, most of the kinetic energy in this flow is in the ions. So if you have ions or protons and electrons with the same velocity because of the difference in mass, most of the kinetic energy is carried by the protons. And so the slowdown of this flow, so the compression of this flow, is dictated by the scale at which these protons will gyrate in the magnetic field. So that's the gyro radius of these protons. Now for an electron, that's a very large scale, okay? So I tried to draw here the motion of an electron that is gyrating around this field line, and the motion of the electron is going to be on much smaller scales than this transition. And so it's very hard for this electron to actually be able to get rid of this magnetic field line and come back and do this shock Fermi acceleration that I was describing to you before. I like to give the analogy of these big wave surfers that I'm sure you've seen in Nazaré, okay? And in contrary to what you see if you go here to, I don't know, Carcavelos or Costa with small waves, you see the surfers just paddling and catching the waves. There's no way they're going to be able to do that in these big waves because their phase velocity is so large that they cannot paddle fast enough in order to catch these waves. And so what do? They use these jet skis. They need to have some injection mechanism. They need to have something that pushes them fast enough or pulls them fast enough that they can be in phase with the wave and ride this wave. So in a sense, we are looking for what is the equivalent mechanism, the equivalent of the jet ski in this shock acceleration. We need some mechanism that can pre-accelerate these electrons until they become energetic enough that their Larmor radius becomes comparable to the shock transition. At that point, they can start entering this Fermi or diffusive shock acceleration mechanism. Now the difficulty is that this depends on physics on the scale of this transition, which are not resolved by astronomical observations. And so we want to understand by other means what's going on at such small scales. This involves a nonlinear interplay between the plasma, the waves, and the turbulence produced in the plasma and the energetic particles at kinetic scales. To understand this, there's a couple of important ingredients that are quite fundamental and that we still don't understand. To start with, we don't know in a collisionless shock how the kinetic energy of the flows gets partitioned between the different populations, electrons and protons or electrons and ions. This is such fundamental that it's very puzzling that this is still not well understood. In a collisional shock, of course, we know that there's time for equilibration between the species. So at the end, they have the same temperature. In a collisional system, this is not the case. So again, imagine that you have a shock here. You have a plasma flow passing by. Initially, all the energy is carried by the protons because they're more massive. As they cross the shock, they get thermalized. Do they do so independently? So the ions redirect their kinetic energy into thermal energy within themselves, and the electrons do the same. If that's true, you would end up with TE over TI or TP, that is ME over MI. So it would be extremely small, which means that the electrons have a temperature much, much smaller than the protons. This would be a big problem because it means that you have to pre-accelerate them a lot in order for them to start being accelerated by Fermi acceleration. If on the other hand we have wave-particle interactions that exchange energy between these two species as the shock is forming and they reach compatible temperatures, then this becomes easier, makes it easier for the electrons to be injected and accelerated. And so it's important that we understand what is the relative temperature between the electrons and the ions behind the shock, and then what gives you the additional boost to the electrons. So what is the mechanism capable of picking some of these electrons from the thermal pool and getting them to high enough energies, then they enter Fermi acceleration, and then at that point you expect a similar acceleration spectrum to develop between both protons and the electrons. But of course, the ratio between these is going to be determined by these processes that we don't understand. This is important because if we primarily observe these supernova shocks by the radiation emitted by the electrons, what is that information telling us about the ability of those shocks to accelerate cosmic rays, protons? If we don't know this relationship, this is difficult. All right, so the goal for now is to tell us a little bit about what we are doing in order to address some of these questions in the context of this ERC project called XPACE, Extreme Particle Acceleration and Shocks, from the laboratory to astrophysics. So the idea here is really to open this complementary view angle, if you want, where we are using kinetic simulations both to model some of these astrophysical environments, but also to connect to opportunities in the laboratory where we could design experiments aimed at studying some of these microphysical processes. And so I'm going to tell you about what we're doing in these two fronts. By the way, I didn't mention this in the beginning, but feel free to ask questions during the presentation if there's something that is nagging you and that you're not understanding. You don't need to wait to the end, okay? So far, so good? Okay. All right, so as I said, we are using kinetic simulations to try to reveal what is the underlying microphysics associated with these shocks. And when we're dealing with first principle simulations of collisionless plasmas, the typical method of choice is the particle in cell method. Some of you may have heard about it. The idea is that you are going to discretize your domain with on a grid, okay? And you're going to push your charged particles on this grid according to the electromagnetic fields self-consistently produced by these particles. How do we do this? Basically, we solve Lorentz force to advance the momentum of these charged particles, coupled with the equation of motion to advance the position of these particles. We then deposit the current density of these particles on the grid. As you know, this is the source term for Maxwell's equations. So from that, we can advance the electric and magnetic fields associated with these particles. We now deposit these fields on the grid so that next time step, we advance the particles self-consistently according to the fields that they produce. So of course quite expensive in the sense that we have to model all these interactions between the different charged particles and the fields that they produce, but it's also a first principle approach to study the basic processes behind these collisionless plasmas. And so let me show you a simulation of what does the formation of one of these shocks looks like. We're going to start with a very simple system where you just have two uniform plasmas colliding against each other, okay? Initially, they are uniform in density. I mean, you have a step, so they start, and then they are uniform, and there's no magnetic field, or there's a very weak magnetic field. In the top, I'm going to show you the density evolution. In the bottom, the magnetic field. This is a symmetric system, so I'm just going to show you half of it. So there's a flow coming from the right to left. There's a symmetric one coming from left to right. And so what you see is that these plasmas start interpenetrating each other. They become unstable. So So you see the development of these filamentary structures both in density, and you see strong fields being produced with these filamentary structures as well. At some point, these fields become strong enough that the fresh plasma that is coming from the right is going to scatter in these fields, slow down, and be compressed. So you see clear a compression region that is moving from left to right. This is our shock wave. Okay? If I now track one of the most energetic particles in the system to learn what this particle is doing, it will look something like this black particle that I have here going around. You see that at some point this particle became lucky enough to be trapped in the magnetic fields near this shock transition, and as it's scattering back and forth, it's gaining energy. And so if I look at the evolution of the energy spectrum as a function of time, you see that initially you thermalize your flow, you have something like a Maxwellian or a Hüttner distribution, and then as the shock progresses, you start developing a nonlinear, a non-thermal tail with a power law type shape. Okay? This instability that shapes the formation of these shocks in the very high Mach number limit, so weak ambient magnetic field, is called Weibull or current filamentation instability. Okay? Let me just give you a quick flavor for the physical picture behind this instability. If you consider two counter-streaming symmetric plasmas, okay, so charged particles moving from left to right, right to left, symmetric, and let's consider a magnetic field with a wave number that is perpendicular to the flow velocity. Okay? As you know, this magnetic field, let's say the magnetic field is perpendicular also to the flow velocity, so it's going to rotate the particles differently depending if they're coming from the left or from the right. Okay? And so this means that a small magnetic field perturbation is going to induce a perturbation in the current, because the particles coming from this side, they're going to be focused in this point. The particles coming from the right, they're going to be defocused. And so this induces a perturbation in the current. And it turns out that the perturbation in the current reinforces the original perturbation in the magnetic field. So we have an instability. Okay? So this leads, even if you don't have initial magnetic field, if you just noise, say because we have finite number of particles, we have temperature, so we have noisy fluctuations in the fields, this instability will amplify these fields exponentially, okay? Until the fields become so strong that they start trapping the particles inside these current filaments, okay? By this process, you can convert a large fraction of the kinetic energy in these plasma flows into magnetic fields at kinetic scales, okay? About 10% of the kinetic energy of the flows can be converted into magnetic fields. This is what we were seeing in the previous simulations. And so we have been trying to understand what is the role that these fields, that these instabilities play in shaping these open questions, in particular the energy partition between ions and electrons and the ability of these shocks to inject electrons. Regarding electron heating, what we find is that this instability is critical in dictating the energy exchange between the ions and the electrons as the shock is being formed. We have our shock front here. We have these strong fields being produced ahead of the shock, where we have reflected ions counter-streaming with incoming plasma. And what we find is that the electrons and the ions that are coming towards the shock will experience these fields very differently. Again, because of the difference in their mass, ions will largely note that these fields are there. They just do small variations in their trajectory, whereas electrons, they become magnetized, and so they become stuck to these field lines. They're going to be decelerated as they propagate towards the shock. And so this the differential velocity between the ions and the electrons gives rise to an electric field and to build up of an electric potential in this shock. And this is what mediates the energy exchange between the two species. Okay? We can do this analytically with a Vlasov-Fokker-Planck type transport equation and show that the parameter that controls this temperature ratio is given primarily by this fraction here. So the ratio between the masses of the two species and the scattering frequencies of the two species in the magnetic fields. And for the case of these magnetic fields produced by this instability, we show that this ratio is between 1 and 10. And so the the resulting temperature ratio is about 0.2 to 0.3. So the temperature of the electrons is a small fraction, but decent one. So it's not 1 over 1800, is about 1/10 of the temperature of the ions. We've also been looking at how these fields enable some of the electrons that have been heated to get injected into a non-thermal tail. Here's an example of the evolution of the electron spectrum behind the shock. So as the shock forms, you see that you start with something that is a thermal distribution, and with time you start developing this power law tail. What we do then is to track a large number of these electrons that become part of this non-thermal tail, and go back in time and ask, okay, how did these electrons manage to end up in this non-thermal tail? What allowed them to do that? And so here's just a representative illustration of a couple of these electrons. You have actually here a symmetric system, so you have a shock wave that propagates to the right, another one that propagates to the left. These curves here are the perpendicular magnetic field energy. So you see that these electrons are gaining energy primarily at this sharp transition, so at the shock front. So they come in, they interact a few times with the shock front, and then they escape. Okay? And so we find that these small-scale fluctuations in the magnetic field happening within this finite distance shock transition are actually very important in allowing these electrons to be energized. This is because the instability is producing magnetic fields on scales comparable to the gyro radius of these electrons, so that they can efficiently scatter them within this shock transition. And so based on this, we propose that at early times in these shock waves, we can have something very similar to Fermi acceleration or diffusive shock acceleration, where the difference is that instead of the particles experience the full jump in velocity or density, because they cannot cross the shock entirely, they will experience a smaller jump, okay, but still converging flows. So they will be able to still scatter back and forth and gain energy as they do that. It's just that the amount of energy that they do in every cycle is smaller because the compression ratio that they feel is also smaller, okay? So these modify the scalings for the energy gain rates, and you see that they are in quite good agreement with what we expect from this modified diffusive shock acceleration model, okay? And so what this is telling us is that if these shocks indeed manage to produce fluctuations in the magnetic fields on small kinetic scales through this type of instabilities, then they manage to inject these electrons efficiently into the shock. Another important question that we've been trying to address is what happened at late times? Unfortunately, even though we can model this from first principles, we are limited in terms of the time scales that we can simulate. Okay? We know that what controls the onset of these instabilities is actually the population of protons that is reflected at the shock. This is a phase space of one of these shocks. So you have here position along the direction where the shock is propagating and momentum of the ions. So the ions are coming towards the shock. A large fraction stays behind the shock and it's thermalized, but a small fraction on the order of 1% is reflected, propagates upstream, and that's the seed cosmic ray population. They will start driving waves, scattering on those waves, coming back, doing diffusive shock acceleration, okay? So what if this fraction changes over time? What if there are other processes that shape the ability of this shock to reflect particles? We see that this is quite important because these escaping protons, they are the ones driving waves. And so in this case, you see that at later times, from what I was showing you before, you start seeing these very strong magnetic fields that are actually right-hand circularly polarized electromagnetic waves that are driven by these escaping protons or cosmic rays. This actually corresponds to a known instability called the Bell non-resonant instability. The idea is that these cosmic rays, they will carry a current, okay? And plasma likes to stay current neutral. So the charged particles from the background, as they start seeing the current from these cosmic rays, they will start moving in order to cancel this cosmic ray current, okay? Because you have magnetic fields now, these, even though the cosmic rays are unmagnetized, the denser, slower particles from the background, they are magnetized, okay? So they will experience a J cross B magnetic force, okay? The cross product between their current and the magnetic field fluctuations. And it turns out that for circularly polarized, right-hand circularly polarized waves, this is going to amplify these initial waves. Okay, so the J cross P force is such that it's going to stretch these field lines. For left-handed waves, it's going to mitigate the initial waves. So actually, this instability only amplifies right-hand circularly polarized waves, which is what we see in our simulations. And so this is still preliminary, but one of the things that we've been trying to do is, okay, let's say that I drive a shock wave like this one, and then at late times, I artificially start injecting a denser population of cosmic rays in my shock. Okay, instead of 1%, I start injecting 3% or 9%. What does that do? So what we see is that that's going to significantly enhance the amplitude of these waves that are driven upstream, and it's going to mitigate the injection of the electrons, as we can see here for this electron spectrum with increasing fraction of cosmic rays injected. This can be understood by the fact that the cosmic rays are driving now stronger magnetic fields on larger scales. So again, the tiny electrons will see this as a very strong uniform magnetic field. It's much harder for them to be able to scatter and to get injected. Okay? So we are still looking into this, but this, if we confirm that this is true, this could have important implications for observations, because this may suggest that supernovae that are very X-ray bright may not necessarily be the best at accelerating cosmic rays. If it's true that when you inject very efficiently protons, then you are going to mitigate the injection of electrons. So we are still looking into this. All right, let me move. How much time do I have, Guillermo?
5 minutes.
5 minutes, okay. Okay. Let me move to the last part. I want to tell you about how we are using also this understanding to try to design laboratory experiments where we can test and validate some of these ideas, okay? Over the last 10 years or so, we've been developing a platform to study these collisionless shocks and particle acceleration at the National Ignition Facility in Livermore, California. This is the highest energy laser system in the world. There's about 2 megajoules of laser energy in about 200 laser beams. How many of you have heard about NIF before? Okay, not that many. Have you heard about this result before? Okay, so about 2.5 years ago, at the National Ignition Facility, for the first time, using inertial confinement fusion, they were able to use all these lasers to compress a tiny capsule of deuterium and tritium in order to release more energy from nuclear fusion than the energy in the lasers that were used to compress and heat this capsule, okay? So this was an important breakthrough for nuclear fusion energy, where for the first time we produced more energy than the one that you input. By the way, if you have not heard about this, just last week, NIF was able to now go from a gain of 1.5, so instead of producing 50% more energy than what was input, to quadruple the energy that was used initially. So we are making quite exciting progress towards higher gain fusion. Now, the interesting connection here is that we can use a facility like this one that is being used to study, for example, nuclear fusion, to use all the energy that we have in these laser beams to produce very energetic plasmas that have high temperatures, very high velocity, so that they are collisionless. And as we collide them, we can produce these type of shock waves and study them, okay? So we are lucky that the facility gives about 5 to 10% of their beam time to the international scientific community, so you can apply for beam time. Unfortunately, it's not much, and so you get to do very slow progress, but it's nevertheless very exciting that we have access to a facility like this one to do some of these science associated with collisionless shocks. And so, as I mentioned, over the last 10 years or so, we've been trying to develop a platform to study this type of shock microphysics. We started with a smaller facility at Rochester called the Omega Laser Facility, where we use the following setup. We have 2 plastic targets. We irradiate these targets with these very powerful lasers, about a few kilojoules of laser energy in a nanosecond, okay? The power associated with this is mind-boggling, okay? It's about 1 petawatt, but it's delivered in a very short amount of time, okay? 10 to the minus 9 seconds. So in terms of energy, it's a few to 10 kilojoules. Now, these lasers are so intense and powerful that as they strike this plastic target, they're going to ionize it, so they're going to produce a plasma, and hit the electrons in this plasma that will drive the expansion of this plasma into the vacuum region outside the target. If we now do this in a symmetric system, we can produce two energetic plasma flows that are going to collide with each other in symmetric conditions, okay? So it's very simple. That's the basic idea behind these experiments, okay? At least conceptually, okay? And so one of the first things that we wanted to study is, okay, if we now produce these very energetic, high Mach number collisionless plasma flows, we collide them, can we see indeed these plasma instabilities producing magnetic fields like we see in our simulations? And so for that, we use a technique called proton radiography. So you know charged particles are deflected by magnetic fields if they are present. So you produce a source here, a control source of protons with very well-defined energy. They will cross the interaction region. If there are no electromagnetic fields, we will just collect them in a radiochromatic film and have a uniform illumination, okay? If there are strong fields, they're going to produce small deflections on these protons, and as we image them, we can infer what the structure of these fields is, okay? On the right here, in the first two columns, we see experimental measurements of this proton radiography diagnostic for 3 MeV and 15 MeV protons. And on the rightmost column, you see the synthetic radiographs simulated in our PIC simulations for the same conditions as the experiment. And so clearly, we see that as these plasma flows collide, they develop these filamentary magnetic fields, okay, that have scales consistent both with linear theory and with the results from these fully kinetic simulations. And so we confirmed for the first time that indeed this instability is present in such environments and can convert an important fraction of the kinetic energy of the flows into magnetic fields at kinetic scales. This was great, but unfortunately, at omega, we don't have a large enough system size that the flows now can interact with these fields for long enough in order to be slowed down and form a shock. And so we had to go to NIF, where we have about 100 times more laser energy, in order to produce a large enough system size where we can see this shock actually form. The setup is very similar, but now we have about 450 kilojoules irradiating each target. We use a set of diagnostics that includes Thomson scattering to probe the density, the velocity, the temperature of the flows at a given location. We use X-ray emission from the plasma to see the difference between, for example, having just one flow or two symmetric ones, where you see with one flow there's no emission. With the two flows, we see very bright, strong emission in the region where they collide. And we have particle spectrometers also to look for particles accelerated by this interaction. Let me be clear about one thing here. The goal here is not to put a supernova in a bottle, okay? That's not going to happen, okay? But you can formally show that the plasma processes that operate at microscopic scales are the same if some plasma parameters are matched between these two systems, okay? We can formally scale the two systems, okay? This is just based on solving Vlasov equation and Maxwell's equations and finding these scalable parameters, okay? And so what is important to note here is that in both these experiments and in typical young supernova remnants, we have flow velocities on the order of a few thousand kilometers per second. The magnetic fields, the density of these plasmas are completely different, okay? But these important dimensionless plasma parameters, such as the collisionality and the Mach numbers, are comparable between the two. And so this gives us confidence that the dominant microphysical processes that we study here are also operating in these astrophysical environments. So what we defined with this experiment. So I'm going to go a bit faster here so that I finish in the next few minutes. We basically show that indeed as these flows collide, they slow down each other electromagnetically, okay, and form a shock. You can see here the velocity of one single flow. So if you just have two of these that don't interact with each other, you get the same result. In red, we have the measurement with the same two flows, but now colliding with each other. You see that they completely slow down as they interact with each other. And we see a strong compression of the density by a factor of 4, which is exactly what you expect from the hydrodynamic jump conditions. So we are forming a strong shock as these two flows collide. And we are seeing that when they do, and they form a shock, we have very energetic particles, in particular electrons, being produced that have energies that are more than 100 times the thermal energy at the shock. So we can measure the temperature at the shock using Thomson scattering, and the energies, that's about 3 keV. The energies that we measure go up to 500 keV, so more than 100 times the thermal energy. So this shock is able to accelerate electrons to more than 100 times their thermal energy. What dictates this maximum energy? If we think about shock physics, this is known as the Hillis limit. The maximum energy is basically dictated by the electric field associated with the motion of these magnetic fields and the size of the system. Okay? And for this, it is exactly 500 keV. Okay, so the maximum energy that we are seeing are consistent with the maximum energy that we expect for shock acceleration with this system that unfortunately just has 5 millimeters transversely. I wish I had some parsec available to do this. We're also being able to resolve the temperature ratio between these species as the shock develops. I won't go into the details, but this is in good agreement with the model that we have put forward last year. And I just want to mention that even though I focus today on the physics of these collisionless shocks, we are also doing work in some other directions that may be of relevance to you, in particular starting to study particle acceleration in relativistic jets and shocks also associated, for example, with black holes, and also trying to learn from these simulations how to derive reduced models for the microphysics. Because what you would like to, in the end, is not to use a kinetic code, is to use a fluid code that is able to model these systems on very large scales, but be able to capture the effect of these microphysics on the large scales. At the moment, unfortunately, this is not possible. So if we learn the dominant microphysics, maybe we can develop better reduced models that we incorporate on the large scales models, okay? So if you're interested in learning more about this or about opportunities to get involved on this type of research, don't hesitate to reach out to me either by mail or after the presentation. Let me just finish here. A lot of this work is motivated by astrophysical observations, okay, which keep revealing that shock waves are extraordinary particle accelerators, but they also insist that we need to understand better the mechanisms behind this acceleration. And what we believe is that the combination between these first principle simulations and laboratory experiments can provide us a new window that is complementary to spacecraft measurements, to astrophysical observations, in order to help put different pieces of the puzzle together and understand how these shocks manage to be so efficient. Thank you.
Thank you very much.